Hello friends, we are going to learn thermodynamics of galvanic cells under this headline gives energy of cell reaction and cell potentials. Now in galvanic cells, work done by that cells is nothing but is equal to the amount of charge passed multiplied by cell potential. But amount of charge passed is equal to what? N into F. So how is this? Because in galvanic cells, number of moles of electrons is required. So that is N, and F is the charge in Faraday. So that is in Coulomb. So Faraday is the charge required. Therefore, electrical work equation becomes like this: N into F into E cell. So cell potentials of this. Now, Gibbs scientists introduce one term, that is delta G. And he concluded that electrical work done by galvanic cell is nothing but decrease in Gibbs energy. So minus delta G, minus negative sign indicates what? Decrease in change in Gibbs energy. And therefore minus delta G is equal to N into F into E cell. So delta G is equal to also minus N into F into E cell. So under standard condition, so this equation becomes like this: delta G naught is equal to minus N into F E raised to naught cell. Okay, so we know that. Now next, we know that delta G is extensive property, but E naught cell standard condition of the under standard condition of that cell potential is not extensive, but it is intensive property. Now how to explain this? So for that purpose, this equation just convert into, for that E naught cell is equal to what? So therefore E naught cell is equal to getting this equation. Now if the stoichiometric equation of redox reaction is multiplied by 2, then amount of oxidized and reduced that substance is increased, that doubled, and therefore delta G also doubled. Okay. Now number of moles of electrons is transferred in galvanic cell, so that also doubled. Therefore you have to multiply by 2 this term. Delta G twice doubled, N into F also doubled. And if you see this equation again, you are getting these two to get cancelled. Then again remaining E naught cell is equal to as it is. So if you multiply by 2, then also redox reaction if you multiply by 2, so again then E naught cell is equal to remain cells. So there is no change. Therefore E naught cell, so under standard condition of cell potential value is an intensive property. Now we are going to learn standard cell potential and equilibrium constant. Okay. Now we know that the relationship between standard change in Gibbs energy of galvanic cell and standard electrode potential is given by what? Minus delta G naught is equal to N F e raised to naught c. Okay, this equation 1. Now the relation between changing Gibbs energy and the equilibrium constant. This is change in Gibbs energy for that the cell and cell reaction, and that for its equilibrium constant K. So what is the relation? So delta G is equal to minus RT ln K. Okay, so this is equation 2. Now you are equating this equation 1 and 2 or combining equation 1 and 2. So getting this term minus F E naught cell is equal to minus RT log to the base K. Now therefore turn this equation for E naught cell is equal to RT upon N into F log to the base C. This is equilibrium constant K, and this term is equal to log to the base E convert into log to the base 10, getting this term 2.03 R into T divided by N into F into log to the base 10 K. Therefore finally the equation you are getting this E naught cell, this is the way. Again if you put down the value of this 2.03 RT upon F, we know this value, that value is nothing but 0.0592. So therefore putting this value getting this equation. So this is that equation. E naught cell is equal to what? This is the one multiple choice question. Which of the following equation is the correct? E naught cell is equal to this, also equal to this, also equal to this. So this is the three forms of equation between standard cell potential and that equilibrium constant, that is K. Now we are going to study reference electrodes. So what do you mean by here reference electrode? Electrodes, reference electrode is defined as an electrode whose potential value is 0, taken as 0, or its value is exactly known. So that is called as a reference electrode. It's known value of that electrode potential. Okay. So in galvanic cells, the redox reaction takes place simultaneously. So one oxidation, another one is the reduction. Both processes take place simultaneously. Therefore, here one single electrode potential cannot measure. For that purpose, two electrode is combining. Then we can measure, because suppose one electrode potential you have to know. Then from this known we can determine the unknown electrode potential, and for that purpose standard hydrogen electrode is a primary reference electrodes. SHC is the primary reference electrode as it determines the standard potential of other electrodes. That's why it is primary. And secondary reference electrodes, for example, that is a silver electrode, piano electrode, or glass electrodes. This is also useful to determine the electrode potential in galvanic cells. Okay, this is the way of that reference electrode. Now, the next point is that standard hydrogen electrode. Just as already seen that the reference electrodes. So, standard hydrogen electrode is a primary reference electrodes. Okay. So, what is standard hydrogen electrode? Already defined in short. Okay. So, the standard hydrogen electrode is an electrode in which pure and dihydrogen gas is bubbled around a platinized platinum plates at 1 atmospheric pressure. Okay. The platinized platinum plate, which is dipped in 1 molar HCl solution, 1 molar H plus ion solution. So that is called a standard hydrogen electrode, SHG. Okay. So SHG is the electrode in which pure and dry hydrogen gas is bubbled around platinized platinum plate, which is dipped in 1 molar H plus ion solution at 1 atmospheric pressure. So this is just that is standard hydrogen electrode. Okay. Now formulation is what? So standard hydrogen electrode, how do you represent? Short notation, that is formulation. So this is your H plus ion. Then the in presence of that is in contact with this H2. Okay. Gas and 1 atmospheric pressure. Hydrogen gas is in contact with this platinum. So this is just representation. This is the representation like this cathodic reaction. Gain of electron takes place. H plus ion convert into H2 gas. Okay. Now look this diagram. What is the given in this particular diagram? Standard hydrogen electrode. Now this is one glass tube. This is glass tube containing this is copper wire. Insert in this. Then another here. This copper wire at the end of bottom of this mercury is insert for that electrical contact. Then platinum wire, the 8 of this, and this platinized platinum plate is joined here. Okay. This solution is the 1 molar H plus ion solution, say for example HCl solution, and this is that at the top this is copper wire, this electrical contact again. Now these two glass tube, pure and dry hydrogen gas being passed into the solution, then there is the bubble creations. So bubble production around that platinum plate. That time what happened? The hydrogen gas is absorbed by this platinum plate, and the some ions that gets converts into that particular the way of that H plus ions. Okay. So the 1 molar H plus ions here around that platinized platinum plate on that plate, this is H plus ions convert into the H2 gas. Now when suppose this is the SHE act as cathode, that time electrode reaction is like this. Okay, because standard hydrogen electrode, when you couple with other electrode, so is it acting as anode or is it acting as that cathode? This depend upon the other electrode condition. Okay, so therefore this electrode reaction at cathode, suppose here at cathode this is happening gain on that electrode, and this is standard electrode potential of hydrogen gas 0.0 volt. What is application? It is used as generally primary reference electrode as it determines the standard potential of other electrode. That's why this is used as primary reference electrode. Now what is difficulties in standard hydrogen electrode? So standard hydrogen electrode difficulty is some problems arises. So what is the first? Number one, it is difficult to obtain pure and dry hydrogen gas. Okay. Now second one is that it is difficult to again maintain. It is not easy to maintain the pressure of hydrogen gas at 1 atmospheric pressure throughout that experiment. Okay. Now because here the some hydrogen gas is here bubbled out, therefore the maintaining of that 1 atmospheric pressure of hydrogen gas is difficult. Now the concentration of H plus ion, this is also difficult to maintain. Concentration of H plus ion to maintain 1 molar condition, again this is due to the some evaporation of water molecules is that also taking place the way of doing this experiment. So this is the difficulties in this standard hydrogen electrode. Next point is hydrogen gas electrode. Now in this case hydrogen gas electrode will present like this formulation of this hydrogen H plus ion aqueous ion is in contact with hydrogen gas, pressure of that H2 gas. Now is in contact with the platinum and this is H plus ion. Here the pressure is not unit, pressure is the differ. Okay. Now electrode reaction is like this. Electrode reaction is just gaining of electron. So gain of electron is this is that cathodic reduction. So H plus ion, aqueous H plus ion convert into hydrogen gas. From the Nernst equation, we know that the Nernst equation is what? Electrode potential of that hydrogen gas is equal to the standard electrode potential of that H2 minus 0.059 divided by up to the base stage. This is that partial pressure of that H2 gas, and that is H plus, this is that is 2 raised to power 2. Okay. So the raised to power 2 like this twice, but 2 is the stoichiometric coefficient there for this. So we know that value of that standard hydrogen potential, electrode potential is what? 0, and therefore only remaining this term minus 0.0592 divided by 2 log to the base 10. This is that pressure of H2 divided by H plus ion concentration of this raised to power 2.